Okay, so welcome to this week's topic on algorithms, AI, automation, and data with Dan Angus. Hi, Dan. Thanks for joining us.
Oh, thanks for having me, Stephen.
So, you can read more about Dan and who he is and what he does here. Could you just tell us a little bit about what you do?
Yeah, so I'm the director of the Digital Media Research Centre at QUT, and my original research and my PhD was actually in computer science. So I've spent largely the past 20 years moving from computer science into humanities and social science. And so a lot of my research and the teams around me, we do research into the intersection of computing technology, these algorithms and society. And so I have a deep interest in how very much we've seen a growth in the role that technology plays in everyday life.
Yeah, yeah. So, what would you describe yourself as now in terms of what kind of research you do?
Look, there's a new field. It's called computational social science. And
Yeah.
I like to think, yeah, I'm a computational social scientist, right? So someone who kind of walks in both worlds.
Yeah, no, that's great. And so that's why I think it's great to have you here to do this because you can give what the aim today is kind of to talk through some of the basics of understandings of algorithms in particular. And when at the end we'll get to a little bit more kind of critical theory stuff. But as
Yeah.
someone like yourself, it's great to have someone with your experience to be able to explain some of these things to a kind of non-technical audience. So yeah, tell us what an algorithm is.
Yeah, so algorithm is a bit of a stand-in. It's a bit of a suitcase concept now because we use it, and I think you're going to talk about suitcase concepts at one point
Hmm.
elsewhere about AI being another one. But algorithms often used as a bit of a stand-in, but it has a meaning in computer science, which is often it's a set of instructions. You could think of it as a recipe or something, or some kind of assemblage of a range of processes put together quite deliberately to achieve some kind of an output. So often you think about these in terms of inputs and outputs. So you provide data or some form of input, and it does something in the middle. There's kind of magic that happens,
Yep.
and then we get some kind of output. So where we see these in everyday life is things like our recommender system. So when you turn on Netflix or you open up your social media, algorithms are deciding what content is kind of making its way to the top. Algorithms are also involved, for example, in removing content. So for moderation, so they're automatically processing, classifying content and taking it out. Algorithms are used to do path routing. So when you're using, say, Google Maps or you're ordered Uber Eats or something, those mapping systems are using algorithms to decide the shortest path between point A and point B.
Yeah.
And so algorithms find their way into our everyday life in a range of ways, but quite simply, they're just mathematical instructions and computational instructions condensed down into some library or piece of code.
Yeah. And so they're playing such a kind of huge role across so many facets of our day-to-day lives now.
And they're just
Should
invisible. They're baked in, right?
yeah.
And I don't think we recognize how many different kinds of algorithms are out there and how we're just coming into contact with them every day in very mundane ways. Like even scanning things through barcode scanners at the supermarket. There are algorithms behind all of this because there are instructions and decisions that are being made as we're interfacing with these technologies. And so
Yeah.
I just want to avail, any of your students around the idea of automatically thinking algorithms equal bad or algorithms equal good. The algorithms are just so, and it's how they're perhaps embedded or used that is more the interesting question to ask.
Yeah, and so let's touch on that because it's like there's questions of trust here, isn't there? Like we have this kind of good versus bad thing going on, and that's all through
Totally,
the course,
totally.
and the course itself is quite like from a critical perspective. So like, should we trust algorithms?
It depends, right? And I think we might get to that in some of the other slides.
Yeah,
So, um, I might unpack on the next slide if you want, Stephen. Yeah.
yeah.
So machine learning, like this is a very particular branch of computer science that revolves around algorithms of a particular form. And this is algorithms which have been designed almost like a blank slate. And so what you've done is you've created a bit of like a tabula rasa. This is something where you've set up the instructions and you want to now train that system to be able to do some kind of formal practice. And
Mhm.
so machine learning is a way to describe this because yeah, you're trying to teach the machine how how to go about its various operations. And so, yeah, you have say a neural network. It has an architecture, so it has a way in which you can feed data in. It has a bunch of things in the middle. We call these weights and connections in how the information flows through that system. And then it has a series of outputs where it's making decisions, say classifications. Is this photo, does it contain a person? Does it contain an animal? Does it contain, a particular kind of food? So,
Yep.
what we're doing though in the middle is we're adjusting those parameters in order to train it to be able to correctly identify or classify an object.
Mm.
And so the essence of this is that it needs lots of data to do it, and it needs lots of labeled training data in order to train those systems. And so whenever we've been doing captures, so click all the boxes that contain a motorbike or a
Yep.
truck or a road or a traffic light, that's us labeling image data. And
Yep.
that data is then being fed into these systems to train them to be able to automatically identify those objects in a visual scene if it's presented to the algorithm.
So
And
the
so
humans in the machine there, isn't there?
exactly. And
Yep.
so this is where the human becomes embedded in the machine a little bit, is that we have been providing the training data for these systems through the ways in which we've been using simple platforms like Instagram and others. If you provide an image, you provide a caption, that information can be linked and used to train these kinds of algorithms. And I'll unpack that a little bit further in some of the examples.
Yeah. Yeah. So can you give me the kind of the distinction between data driven and logic driven?
Yeah, so this is really distinguishing between, like, with algorithms, we often have designed them in the past quite deterministically. So we kind of come up with a set of rules, we know what we want them to do. And that's a kind of what we might think of as a top-down logic. And so in the example here is like, these are all capital letter A's. But if I was to ask you, what is a rule that you could tell a machine to recognize what a capital A looks like? That's a really hard thing to do deterministically. So that's like the right-hand side where you think, okay, it's two,
Mm.
sloping lines in it, some
Yep.
kind of grave in the middle, that would create an A. But is that going to capture all that diversity on the other side there? And so that's where machine learning has really become so popular. Is
Yep.
because in our natural world there is so much variation, and it's really hard to deterministically capture what every encounter or every object or every experience is going to look like. And so it's more that we do this bottom up now through these open systems that we train, is to find all the variation in the natural world, put that into the machine, and then have it figure out and discern the rules itself within its internal logics.
Yep. Yep. Okay. So yeah, let's tell us a little bit about
So
this.
math, right? I couldn't help myself. You need to put some math here. This is at the heart actually of all of the machine learning that we really talk about. So this is and this goes back. We're talking middle of last century that Rosenblatt developed this Mark I perceptron. And what it was, and this is just to demystify this a little bit, is that at the heart of any of these algorithms is just math, right?
Yep.
And it's actually quite simple math, but it's scaled and chained in a way that it can do extraordinary things. And so what you see here is on the left-hand side is the inputs to the system. So that's the x1, x2, xn. They might be like a pixel in an image, right? So you've taken an image apart, pixel by pixel, and there's a value there for each pixel in terms of its RGB value, and you're putting that in. Then you're multiplying it by a weight, and that's the training part of it. The machine learning part is how those weights they're set.
Mm.
And then what happens is all that information is just collapsed and condensed and summed together, and then it's squished between 0 and 1 through that other funny looking kind of
Yep.
what we call an activation function, and then it's output, and then it goes to another one of these, and another one, and another one, and another one, and they feed them their way through that whole neural network, eventually getting to an output layer where we discern, yes, is this a dog? Is this a
Yep.
car? But at its heart, these are just, yeah, it's simple mathematics.
And the perceptron is kind of like making it's like making it more like accurate on the way through. Is that how it works?
So it's tuning it, right? And this is the
Tuning.
tuning element of these systems. And it's just to kind of reveal, and not that you would need to understand how any of this really works, but it's like sometimes we think, oh, it's just magic.
Yeah.
No, it's just math, right?
Yeah.
It's just these are the simple building blocks which, when added like, and you're talking now in some of these neural networks, thousands upon thousands, in fact, millions of these
Mm.
daisy chained and configured through,
Yep.
that's where you get the emergence of this ability to do these fairly profound things in
Yep.
terms of classification or indeed now generative AI as well. But at its heart, very, very simple building blocks, and that's what Rosenblatt's Mark One perceptron was. This whole configuration, he called it the perceptron.
Okay. So
So
tell us
yeah,
about how the artificial neural networks work.
yeah. So you take, just as I said, that neuron, that perceptron, and then you connect it, right? And what you have is your input, you have your output, and you have multiple layers in the middle. We call these hidden layers. And
Mhm.
so this is very much just about, yeah, taking any kind of media input. It could be audio, it could be text, it could be image, and then you're thinking about what is the way in which you want to classify this, sort this in some way, and the middle piece is where the training or the learning happens. It's in that those weights that I was just showing you and all the connections, in fact, between these are pruned or added, and then that leads to a trained network which is able to do things like, yeah, classify text or
So,
classify
so could you
image.
describe using an example of, for instance, we wanted to build a machine to identify cats?
Yeah, so what you would do is you would get a huge database of images of cats, but you would also get a huge database of images that don't have cats, right? So you need the presence and also the absence. You would take those images, you would split it. You would have what we call a train set and a test set. You would run the images through that network in one direction, and what you would see is as you put in images of cats or not cats, is the output correctly predicting these correctly or not?
Mhm.
And depending on how it's classifying those, you'll then make slight adjustments. And as you're making adjustments, you're going to see, is it getting it better or worse, right?
Yep.
Is it guessing, above chance or below chance? And you're going to tweak those values in the middle until you get the highest classification accuracy possible. And once you do that, you would then take the data that you haven't actually seen yet, so the test data that you kept off in a safe somewhere, and you're going to run that through. And that's going to tell you, have you over specified and over generalized on just the training data, or have you done a good job of abstracting what makes a cat, right, within that image? And
Yep.
is the neural network well trained to be able to determine that?
Yep.
And so those processes, that's what we have often used, is this algorithm called backpropagation. But there are many now available that do this form of learning quite efficiently, and in fact, it's at a huge scale. So it's not just like one category. We're talking about thousands upon thousands of categories that are able to be trained simultaneously.
Yep. Okay. Right. So yeah, can you tell us here about the deep
Yeah.
learning
So
computer
this
vision
is
recipe?
just like to kind of make it clear to your students that this didn't just happen in an instant, right? And there are a few things that came together to allow the kinds of forms of this machine learning and the AI phenomena that we're dealing with right now happen. And that was, we had the emergence of big social data sets. So ImageNet is an example of that, and there are many others.
Hmm.
And this was largely through to the participatory nature of the internet, that we had all of us creating huge amounts of data, right? So we were sharing photos, we were labeling those photos, we were sharing lots and lots of information. And so those data sets were able to be amassed in a scale that you need to train the system. We also got a breakthrough then in the ways in which we train those systems. So that algorithm I was talking about, of how you actually adjust the knobs and dials and such, there are millions of these hyperparameters. And so you can't do that by hand. You need an algorithm to actually do that training. And there was a breakthrough there in how we do that as well. But then the other part was that there was the development of these particular chips, right? These GPUs that were largely used in computer graphics. But it turns out the architecture of those is very, very well suited to these kinds of training paradigms. And so they're able to optimize the training for these GPU chips. And so we got this a magnitude of order speed up
Mhm.
in the rate of training. And so it's all these three things that come together to allow you to get these like learned weights to train one of these networks to be able to do these kind of superhuman feats.
Yeah, yeah. So I can imagine in my own head like how it's done with photos of things. How does it work with, say, a song? Say
So
for how, say, Spotify works.
yeah, so songs are interesting because songs, it's all about the temporal ordering. And there was a branch of these neural networks that some figured out that were able to take account of that temporal sequencing.
Right.
And so that idea that it wasn't just about one image that just feeds through as one block of data. Rather, it was more that attentiveness towards a song. Its meaning comes from the sequence of information. And so if you think about every bar or every moment in a song, we there was an architecture and a learning paradigm created for that architecture. So you had the network itself and the neurons that could deal with that and deal with that sequence nature. But then you had an algorithm that could train that and take account of that. And it was through this idea called recurrence. So if you think about what I was just showing with that Rosenblatt perceptron, it looks like it's all one direction.
Mm.
Well, what these did is say, well, do that, but also have connections that go back, right? So you can actually have it's almost like a reverb pedal, right, inside the network, and you could actually have then information floating and sustaining inside the network from time zero to time one to time two to time three, and it meant that it could start to abstract and learn those sequences, so it could understand beat and other kinds of melody
Yep.
within the song. I say understand, like it could abstract it,
Yeah.
right? It could learn a representation of
And
that.
categorize it.
Exactly.
Yeah. Okay. Okay. So thanks for that. That's good to kind of be able to get a kind of 101 of the kind of basics of how this stuff works. Moving a little bit now to kind of the kind of social science part of the computer social scientist. And
Yeah.
there's throughout the history of sociology and social science generally, there's been this idea of technological determinism. And there's obviously a critique of technological determinisms now. So the course itself, I think, is set up very much from a critical orientation towards AI and algorithms. I want students in the course to think critically about these things because they're so important to our day-to-day lives. But there's a kind of a mistake to be made by going too far, isn't there, to kind of say that these things are kind of determining how we live and deciding who we are and making us be certain things.
Yeah, and I always get it. Like when you read the media around technology, it's when you've got framings like such and such causes, right? Like, the technology caused this. And it's like, no, 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 let's be careful here. Let's think carefully about how technology itself is implemented, the cultural and structural conditions in which it's
Mm.
made available, and how you need to think about that as much as you need to think about the technology itself.
Yep.
The classic case I see all the time is how a multitude of society's ills is just foisted on social media, right?
Yep.
And as if like, disinformation or misinformation, it's social media is the problem. I'm like, that doesn't really unpack the idea of the cultures that inhabit that and how those cultures are supported by perhaps parts of the design of the algorithms and the system itself. But you still need people in those roles acting in certain ways, right? So
Mm.
this is it. It's like you've got to be careful, and that duality is always there. That you're not just talking about the technology divorced from the culture.
Yeah, yeah, and so there's social media was a good example. So in the kind of banning debates, that just
Yeah.
completely cut out of that debate was all the positive things that social media provides young people, the way that people, that may be marginalized or bullied can find people like themselves, and create communities and scenes and support, right?
Yeah, and ultimately the complexity of it, right?
Mm.
That these are complex, and that's
Yeah,
your use of social media, Stephen, my use is going to be very different to your students' use, and
yeah.
those patterns, those regimes that we use are very, very different, and
Yep.
so it's very dangerous because sometimes what this also does is where we lean too far into technological determinism, we kind of give over power, right?
Mm.
We say that ultimately the only way to fix it then is to design a better algorithm or to give more power to those companies. I'm like, well, hang on. I don't know that's necessarily correct, right? There are cultural like ways in which we can address this culturally, socially, or in other ways, and it's not always a tech fix is seen as like the silver bullet.
Yes. Yeah. That's great. Thanks. So yeah, what's algorithmic culture?
So Ted Strauss and others kind of talked about this in the way that you've got this emergence of computational systems and algorithms also starting to do things. And this is really I'd say it's like in the 90s and the noughties, we start to see more and more of this, but particular with Web 2.0 and the emergence of a lot of the ways in which social media platforms particularly started to use recommender systems or engage in ranking and sorting, remembering that social media used to be very much temporal feeds, right? Like we
Mm.
didn't have the algorithm deciding what information got boosted
Yep.
or flattened. And so Professor Strauss and others were really interested in this in terms of how computer algorithms started to be turned towards the stuff that was traditionally human, right? The work of the DJ or the work of the literary critic or the librarian, right? The sorting and classification and that hierarchy of objects and things. It became to be something that algorithms were more involved in than ever before,
Yeah.
because that task, the taste making there, was always seen as something that was innately human. You needed a human to be the person that
Mm.
dived deep in that catalog of records to go, oh no, this is the song that you want to hear right now. Whereas now we have algorithms doing that through Spotify and other streaming platforms that are pretty damn good actually in some ways, but I would still say limited in others.
Yeah.
But yeah, algorithmic culture is that it's that duality of how
Yeah.
algorithms play more of a role in determining culture, but how we also reinforce it.
Yeah. Okay. And the last kind of concept I'd like you to um, reflect upon is the problem with big critique. And you kind of
Yeah,
touched
so
upon aspects of this already. Yeah.
yeah, good, good. Because I mean, this is work. Jean Burgess is a good colleague here at QUT, of course, but others, yeah, Kath Albury, Anthony McCosker, and Ron Wilkin write about in their book. And it's really that idea of, and this goes to that technological deterministic claim as well, that
Mm.
we sometimes find ourselves between these two extremes. And one is that shut it all down, it's all terrible, society's collapsed because of these things. And so, and data valence and all the badness, right? And that's what is often termed as like big critique. It's an inflated claim that is made perhaps on one side, the other side, which is that the technology can save us, it can do everything, AI is going to revolutionize the world, blah, blah, blah. But it's met with this increasingly polemic take on the other side.
Yeah.
And what that often does is it inflates the ability of the technology. And that's really dangerous because if we just allow the technology to fail on its own, you would then see in the middle here, well, actually, it's not omnipotent and it's not all powerful. And in
Yeah.
actually fact, my recommender system is pretty crap.
Yeah.
It frequently doesn't do this thing. But because we often inflate it in the polemic hot takes on the other side, it actually creates a condition where we think about, well, oh, geez, really, it can do all this. We panic, we create that kind of, triggered response, and we're left kind of in this really really bad way where we're not
Yeah.
thinking critically about, well, realistically, what is the everyday impact of this.
Yeah. Yeah. It really resonates with kind of moral panic kind of critique, doesn't it?
100%,
Yeah.
100%, it's exactly in the same frame.
Yeah. Okay. So I think I've got to the end there. So thanks a lot for your time, Daniel. And I know you're going to join us again in the course to talk about tuning machines, and I'll talk to you again there.
Look forward to it. Cheers.
Ben, cheers.